Hello everyone, welcome to Math Enthusiast channel, and for today's video, we will solve this integration problem posted by IntegralSpot from Twitter. And to start with this problem, let us recall the concept of not complex logarithm. So complex logarithm. So here complex logarithm is given by this identity, complex logarithm. So complex logarithm is ln of some complex function, let's say a plus I times b is equal to 1/2 times ln of a squared plus b squared plus I times arctangent of b over a. So this is the complex logarithm identity. So using this formula, so the imaginary part of this complex logarithm is this one, which is arctan of b over a. So if we apply this identity to this integral, we will know that this is the imaginary part of some complex number. Let's say this is the a and this is b. So if we will apply this, then let him denote the imaginary part. So integral from 0 to pi of ln, this is our a, which is x, so x, and b is ln of sine x, so x plus I times ln of sine x dx. And if we will factor this imaginary number, which is I, factor this out, then we now have imaginary part of 0 to pi of ln I plus ln 1 over I, this is 1 over I times x plus ln of sine x, this is 1 over I, and here. So the value of this is equal to I times pi over 2, which is derived from the Euler's equation, which is the e raised to I times pi over 2 is equal to I. So if we will take the natural log of both sides, we will have I pi over 2 is equal to ln of I. So here, so taking the imaginary part of this is pi over 2 and multiply it to the pi, because if we will integrate this function ln I, and this will only result to pi minus 0, which is equivalent to pi. So this is pi squared over 2 plus imaginary number of, and we know that 1 over I is equivalent to negative I. So integral from 0 to pi of ln negative I times x plus ln of sine x dx. So here, so using the formula of Euler's for trigonometric functions, we know that sine x is equal to e raised to ix minus raised to negative ix divided by 2I. So if we will use this identity for this integrand, then pi squared over 2, and also I just want to add that negative ix is just equivalent to ln of e raised to negative ix, which is the same as negative ix. So yan. So plus imaginary part of integral from 0 to pi of ln times ln of e raised to negative ix plus ln of e ix minus e negative ix divided by 2i dx. And by the property of logarithm, adding this to natural logarithm will result to multiplying its argument function, which is e raised to negative ix times this function e raised to ix minus e raised to negative ix divided by 2i, and this will only result to pi squared over 2 plus imaginary part of and 1 minus e raised to negative 2ix divided by 2i dx. So here we just multiplied this function and this function, and it will result to this. So now, to get rid of these natural logarithms or some iteration of natural logarithm function, so we will get rid of this by using the partial derivative concept. So if we will notice na we can put a function here, let's say limit as a approaches to 0 and integral from 0 to pi ln of 1 minus e raised to negative 2ix divided by 2i and multiplied by ln raised to a of 1 minus e raised to negative 2ix divided by 2i. So notice, as a approaches to 0, this will become 1. So this is valid. This is a valid step. So notice also that this expression is just the derivative of ln of 1 minus e raised to negative 2ix over 2i raised to a. So this is just the derivative with respect to a. So using that fact, then pi squared over 2 plus imaginary part of limit a approaches to 0 and partial derivative with respect to a. Of course, we will take the first derivative of this function with respect to a, and from 0 to pi of, and we are now left with this expression or integrand. So ln a 1 minus e raised to negative 2ix divided by 2i dx. And also, to get rid of this, let's introduce another variable, which is b, and pi squared over 2 plus imaginary part of limit as a approaches to 0, partial derivative with respect to a, and limit as b approaches to 0, and integral from 0 to pi and ln of a 1 minus e raised to negative 2ix divided by 2i times 1 minus e raised to negative 2ix divided by 2i raised to b dx. So this is our new expression, which is introduced with a new variable, which is b. So notice also that as b approaches to 0, this will become 1. So this is also a valid step. So, and also notice that this expression here, ln of 1 minus e raised to negative 2ix over 2I raised to a is just the 8 or a, let's say 8 derivative. So here using this, we now have pi squared over 2 plus imaginary part of limit as a approaches to 0 and partial derivative with respect to a, and limit as b approaches to 0, and partial derivative of b, partial derivative of b to the 8th order. So here we now have we are now left with this simple expression, which is this. So 1 minus e raised to negative 2ix over 2I raised to b dx. So now we can integrate this function easily using the binomial theorem or binomial series of Newton. So what is the binomial series? So binomial series is given by the formula of 1 plus c raised to d is equal to sum from k is equal to 0 to d of this is the binomial coefficient and c raised to k. So this is the binomial series. Using this formula for this function here, then we now have pi squared over 2 plus imaginary part of limit as a approaches to 0 of partial derivative with respect to a, and limit approaches as b approaches to 0 of limit of derivative of b to the a order. So this is 1 over 2b times I raised to b, and then followed by the employment of this series, which is binomial series. Then this is just b is k and b. This is the binomial coefficient, and negative 1 raised to k and e raised to negative 2ixk dx. So now to avoid the undefined term here, we will expand this series and adjust the index limit, which is from k is equal to 0, we will convert it to k is equal to 1. So by doing that, this is now pi squared over 2 plus imaginary part of limit as a approaches to 0 and 1 over 2 raised to b I raised to b times, this is the first term at k is equal to 0. This is just equal to 1. So 1 plus b k, and just copy the argument of sum, which is negative 1 raised to k and e raised to negative 2ix k dx. And we can distribute this this factor inside this one, and by doing that y squared over 2 plus imaginary part limit as a approaches to 0, a limit b approaches to 0, this is 1 over 2 raised to b times I raised to b plus 1 over 2 raised to b times I raised to b times sum from k is equal to 0 to b of binomial coefficient bk negative 1 raised to k e raised to negative 2ix k dx. So if we will integrate this is just pi. So pi squared over 2 plus imaginary part limit as a approaches to 0, a limit as b approaches to 0, sorry, this is now pi raised to pi over 2 raised to b times I raised to b plus sum from k is equal to 0 to b k negative 1 k 2ix k dx. So notice that this integral will approach to 0. So you can do it by yourself, and I will not include this because my paper is already full. So we will just include that this integral is going to 0, and using that, then we are now left with pi squared over 2 plus imaginary part limit a approaches to 0, partial derivative with respect to a, limit as b approaches to 0, partial derivative of b to the a order of pi raised to pi over 2 raised to b times I raised to b. So now we have very simple expression, and we can evaluate this without so by evaluating this, first we will get the derivative of this expression to the a order. So we will first factor out this constant factor, which is pi, outside the imaginary part. So this is equal to pi squared over 2 plus pi times imaginary part of limit as a approaches to 0 and b approaches to 0, and the derivative of this function to the a order is just negative ln of 2i raised to a, of course. So 2 raised to b times I raised to b, and as b approaches to 0, so we know that it is obvious that this will become 1. So this is 1. So we are now left with pi squared over 2 plus imaginary part of limit as a approaches to 0, partial derivative with respect to a of negative ln of 2i raised to a, and taking the derivative of this expression with respect to a, this is equal to pi squared over 2 plus imaginary part of limit as a approaches to 0 of ln of negative ln 2i times negative ln of 2i raised to a, and as a approaches to 0, this will be equal to 1. So we are now left with pi squared over 2 plus, sorry, I didn't include pi here, there's a pi outside, and pi times imaginary part of this very simple expression, which is natural log of negative times natural log of 2i, and this is equal to negative pi times arctangent of 2 times ln of 2 divided by pi. So this is our final answer to the problem. So I hope you like this video, and don't forget to subscribe and share this to your friends so that they can learn something from it. So thank you, and God bless you all.